Hey everyone, welcome back, and today let's solve Leetcode problem 1304 titled Find n unique integers that sum up to 0. So pretty straightforward problem statement here. We're given an integer n and we need to return any array possible that contains n unique integers. So basically all of them have to be distinct from one another such that the total sum of all of the integers in that array sum up to 0. Right? So in example 1, we have our input n to be 5, and what that really means is we have to return 5 unique integers, either negative or positive. Of course, we have to have negative integers, and I'll explain why in a minute. That basically have a collective sum of 0. In this case, negative 7 plus negative 1 plus 1 plus 3 plus 4 has a collective sum of 0, and so this would be accepted. The same property is also with these two arrays. They also would be accepted, right? For example 2, we only need 3 integers in our array, and notice how there's actually a neat pattern here, right? We have 3 integers. 0 is not going to affect our sum, right? It's just going to be that kind of neutral element because, of course, our collective total has to be 0, and 0 isn't going to do anything. It's not going to hurt us. It's not going to help us. It's just simple. It's just neutral. Negative 1 is going to give us a negative sum, but to counteract negative 1 and to get back a net sum of 0, we'd need its positive counterpart, which would be the absolute value of it, which would be 1. Notice how 1 plus negative 1 is going to be 0, and this 0 is just serving as a neutral value, right? Any value, again, this is leading to the key observation that we need to make, any value can counteract the value of its absolute value to form a collective sum of 0. That, which again, won't really actually affect this total sum of our array, right? Which is what we're going for, and there should be negative value here. Right? And again, for example 3 here, this is kind of an edge case. N is just 1. We only have one option, and that is the only element that doesn't actually give us a non-negative or positive sum, and that is 0. And notice how for any time we have an odd number of integers, we would have pairs of values that counteract themselves with their absolute counterparts, but then we'd have one value left over because we have an odd number for n. And whenever we have an odd number for n, we can just use 0 to make that our last and final neutral value, right? And we're going to go more in that later. But so as you can see, the constraints here are actually rather small here. We only have n to be from 1 to 1,000, which leads us to the main observations that we really need to make here. Basically, for all of the n integers that we need, we know we can form an even number, or n minus 1 integers, using just n-half pairs of elements. And these n-half pairs are going to be formed by every negative value and their corresponding counterpart to get a net sum of 0. And if n is odd, meaning we're going to have one last element that we need to take care of remaining, we can just make that 0 because that would be a neutral sum that would still contribute nothing to our overall net sum of 0 to get that collective sum of 0. And even easier, if n is even, we don't even need to add that 0. We can just use the n-half pairs of elements and their corresponding absolute value counterparts to get a total collective sum of 0, because that is a key observation that we need to make. Negative 7 and 7, negative 6 and 6, negative 2 and 2, negative 3 and 3, all of these counterparts or all of these pairs form a net sum of 0, right? Which brings us to the main kind of part of the solution, and that is the coding solution. So before we even start iterating through our n-half pairs of elements that we choose from, let's first initialize our resulting list, and this is going to be an empty list. This is effectively what we're going to return at the end of our code. This is going to contain the n actual integers that have a collective sum of 0 once we process all of the pairs, and the leftover 0 if n is odd, which we handle at the end, right? So for I in the range, we'll start from 1, and we'll go up until n-half. Why? Because we only need n-half pairs, as in each iteration we can take care of a pair of elements, a negative value and its corresponding absolute value counterpart, which accounts for 2 values in each iteration. And we're going to do +1 to count for the +1 offset for for loops in Python for the second parameter. So really this is going from 1 to n over 2. And this is integer division, this double slash here in Python. So for every value, we're going to, rather iteration, we're going to add to our result I, and then we're going to add to our result negative I. Because I plus negative I is going to give us a net sum of 0. And mathematically, I plus negative I is just equal to I minus I, which is just equal to 0, which does nothing to our total collective sum. It's just a net sum of 0, which is at the end of the day what we're trying to do, as our problem statement tells us, right? So that's what we do for every pair of elements, and that we're going to have n half pairs because every pair has 2 elements. But what if n is odd? That's the next case that we have to handle. If n modded by 2 has a remainder result of 1, that means it's odd. And so if that's the case, we haven't taken care of one last element. We've only covered n half elements minus 1. We have to take care of that last element. And so the way we do that is basically just add to our results 0 at the end, because 0 is going to be that final neutral element that won't actually change our sum. For example, when n was 3 here, we had one pair, which took out 2 elements. So we had 3 minus 2 elements taken care of, but we had one last element left, which we just added that 0 in the array to take care of that, which wouldn't actually change our sum. It would still keep that same net sum of 0 property as it would be that kind of neutral value, just to make sure we fill all n integers if we had an odd value for n. And effectively, at the end, we simply return the result as the final list of all the n integers that have a collective sum of 0, right? So unless I made any syntax 0, 0, this should be accepted, and this should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, we're basically iterating through all the n half pairs of elements that we can kind of form. For each pair, we're going to have 2 elements, the negative value and its corresponding counterpart, absolute value, to have a net sum of 0. And if n is odd, we'd have one element left over that we haven't actually added or taken care of to our result, and that would just be 0 to ensure that our net sum continues to be 0. Which brings us to the memory or space complexity of the solution, which are both really just going to be linear, right? The memory complexity here, or the space complexity, is going to be big O of n, or linear. Why? Because this extra auxiliary memory or data structure list result is going to be having, exactly n elements, which is why it's going to take up an extra space of big O of n. And the runtime complexity here is also really technically just a simplified big O of n, because technically, even though we have n half iterations, that simplifies to big O of n because we don't care about coefficients or constants in runtime complexities, right? So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.